Look at whatever's directly in front of you right now. Like maybe it's a wooden desk or the steering wheel of your car or even just the smartphone you're holding in your hand. Give it a tap.
Yeah, you expect it to push back.
Right. It feels perfectly solid. It has weight. It undeniably takes up space. I mean, we use words like mass, weight, and matter interchangeably every single day to describe this reality, but
It's almost entirely an illusion.
exactly. Welcome to our deep dive into the source material on mass and matter. And our mission today is basically to dismantle that reality you're looking at. Because when you actually look at the modern physics outlines we're diving into today, it becomes clear that almost every intuitive assumption we make about the physical universe is, well, it's completely backwards. That desk isn't a solid object at all.
No, not even close. The deeper we look into the physical universe, the more that everyday sense of solidity just breaks down completely. The materials we take for granted are actually just these vast expanses of empty space governed by really bizarre quantum rules.
And the weight we feel.
The weight is largely just the byproduct of chaotic invisible energy. So if you want to understand what the universe is actually made of, we have to strip away all those assumptions we rely on just to, walk through a room without freaking out.
Which is, yeah, that's a lot to wrap your head around.
Yeah.
But I think the best place to start dismantling those assumptions is with the most fundamental mix-up of all, which is mass versus weight.
Oh, absolutely. The classic misconception.
Right. So let's say I put a 50-kilogram iron block on a scale here on Earth. The scale pushes back with about 491 newtons of force to keep that block from falling through the floor.
Which is its weight.
That force is its weight, exactly.
Yeah.
But if I take that exact same 50-kilogram block to the moon, its mass hasn't changed, right? It's still 50 kilograms of iron.
Right, but the moon's weaker gravity only pulls it down with about 81.5 newtons of force, so the weight changes drastically.
Because weight is...
Weight is entirely circumstantial. It is literally just the local force of gravity acting upon an object. But mass is an intrinsic property. It belongs to the object itself, regardless of where it happens to be in the universe.
Okay, so if I'm floating in the dead vacuum of deep space, like far away from any planet, my weight is zero.
Zero. You're completely weightless.
But I still have mass.
Exactly. And in classical physics, mass is fundamentally about inertia. It's the resistance of an object to any change in its state of motion. So even floating in deep space, if someone tries to push you, they still have to exert effort to accelerate you. Your body still resists being moved. That resistance is your inertial mass.
Like pushing a stalled car.
Right.
If I try to shove a stalled car horizontally on a sheet of slick ice, it's really hard to get it moving, even though I'm not lifting it against gravity.
That is a perfect analogy, yeah. That resistance to your push is inertia.
But this brings up a contradiction from the sources that apparently bothered physicists for centuries.
Oh, the equivalence principle.
Right, because inertia is a resistance to being pushed, like the car on the ice. But gravity is this phenomenon of mass being pulled down by a giant celestial body. Those are two totally different physical concepts.
Completely distinct theoretically.
So why on earth do we use the exact same scales to measure them? Like, why should the property that makes a car hard to push be mathematically identical to the property that makes it heavy?
Well, the short answer is classical physics offers absolutely no theoretical reason why they should be identical.
Wait, really? None?
None. It is purely an empirical observation. It's known as the equivalence principle. Inertial mass and gravitational mass just happen to be exactly the same. And I mean exactly. We've proven it experimentally to 1 part in a trillion.
That is wild.
Yeah. And Galileo was actually one of the first people to rigorously test this, not by dropping things off the Leaning Tower of Pisa, like the folklore always says.
Right, the myth.
Yeah, he actually measured this by rolling bronze balls of different masses down these really smooth, parchment-lined wooden ramps.
Parchment-lined, wow, so he could reduce friction.
Exactly. And because mechanical clocks just weren't precise enough back then, he used a water clock. He literally weighed the amount of water that flowed out of a vessel during each descent.
That is incredibly clever for the time.
Right. And he found that the acceleration was constant. It was completely independent of the mass of the ball.
And then centuries later, astronaut David Scott proved the exact same thing on the moon during the Apollo 15 mission. I love this part of the source material. He stands out there in a vacuum, drops a heavy geological hammer and this light falcon feather at the same time, and they hit the lunar dust at the exact identical moment.
Because gravity pulled on them equally relative to their inertia. It's this incredibly precise coincidence, and it's actually the entire foundation Einstein used to develop general relativity.
Because he treated gravity not as a pulling force,
But as the curvature of space-time created by mass. If gravitational and inertial mass weren't identical, relativity just wouldn't work, period.
Okay, so if mass is this fundamental, universal property that breaks space-time, it creates a huge practical problem for humanity. How do we standardize a measurement for it?
Yeah, that was a mess for a long time. Historically, we had to rely on biological baselines.
Like the carob seed.
Exactly. The ancient Romans defined their measurements using the carob seed, which, fun fact, is the origin of the word carat that we still use in gemology today.
Oh, I didn't know that.
Yeah, they standardized the Roman pound as being exactly 1,728 carob seeds.
But wait, a wet season gives you heavier seeds, right? And a dry season gives you lighter ones. You can't run a global scientific community, let alone calculate planetary orbits based on farming yield.
You really can't, which is why by the late 18th century, science realized it needed absolute precision. And this leads to Henry Cavendish in 1797. He performed this astonishing experiment using a torsion balance to essentially weigh the entire planet.
In 1797?
Yeah, over a century before the electric light bulb.
That's insane. How did he do that?
Yeah. He suspended a horizontal wooden rod from a wire, and he put small lead spheres on each end of the rod. Then he brought these massive lead weights really close to the smaller spheres.
To measure the gravity between them.
Exactly. The microscopic gravitational attraction between the lead spheres caused the wire to twist ever so slightly. By measuring that tiny, tiny twist, Cavendish calculated the gravitational constant. And from that, he figured out that the Earth's density was about 5.48 times that of water.
Just from watching a wire twist in a shed.
Right. But even with that level of mathematical sophistication, the actual physical standard we used for the kilogram was still remarkably primitive.
Oh, the Paris cylinder.
The international prototype of the kilogram. In 1889, the global scientific community locked a single cylinder of platinum iridium in a vault outside Paris. For 130 years, the definition of a kilogram was literally just
whatever this specific piece of metal weighs.
Yeah, that's it.
But physical objects change. I mean, it gets scratched, it collects dust. Over decades, that cylinder has to absorb microscopic contamination from the air or, lose a few atoms when someone wipes it down.
It was drifting. And that's a massive problem because the kilogram is a base unit. Other fundamental measurements, like the Newton for force or the joule for energy, derive from it.
So if the metal cylinder in Paris loses a microgram, the definition of energy for the entire universe effectively shifts on paper.
Yes, exactly, which is terrifying for physicists. So to stop the drift, we completely redefined the kilogram in 2019. We literally threw out the metal cylinder concept and tied mass to invariant constants of the universe, specifically the Planck constant and the speed of light.
Okay, but how does that actually work in practice? I can wrap my head around a metal cylinder, but how do you weigh something using a quantum mechanical constant?
Well, we use a highly complex instrument called a Kibble balance.
The Kibble balance.
Yeah. Instead of balancing an unknown mass against a known physical weight on a traditional scale, a Kibble balance balances the mass against electromagnetic force.
Oh, interesting.
It runs an electric current through a coil of wire suspended in a magnetic field. By measuring the current and voltage, you need to exactly counteract the downward pull of the mass and using quantum electrical effects like the Josephson effect.
You can calculate the mass using the Planck constant.
Precisely. The baseline for mass is no longer a physical object. It is a fundamental law of physics.
Wow. Okay, so we finally perfected the ruler. We figured out how to measure it flawlessly. But the source material really pushes us to ask what exactly it is we are measuring. Because what even is matter?
That is where things get genuinely weird.
Yeah, because when we move past the classical view of matter, like atoms looking like little solar systems, and we zoom into the subatomic scale, the idea of a solid object just vanishes.
Completely. Ordinary matter is composed of elementary particles called fermions, the quarks that make up protons and neutrons and the electrons orbiting the nucleus. These are all point particles.
Point particles, meaning they have mass, but they have zero volume.
Zero volume. They take up no physical space themselves.
Okay, stop right there. Because if my disk is made of point particles with zero volume, and the distance between the nucleus and the electron is vast, mostly empty space,
which it is.
Then why doesn't my hand pass right through the wood? Why does it feel so hard?
Because the resistance you feel when you push on the desk isn't the physical collision of tiny billiard balls. It is the Pauli exclusion principle in action.
The Pauli exclusion principle.
Yeah, it's a fundamental rule of quantum mechanics. It dictates that no two identical fermions can occupy the exact same quantum state simultaneously.
So they literally can't overlap.
Right. So as your hand presses into the desk, the electrons in your skin are being pushed closer and closer to the electrons in the wood. Because they are forbidden by quantum law from sharing the same state, their momentum uncertainty must increase, according to Heisenberg's principle. This mathematically forces them to repel each other.
So the desk isn't solid because the matter inside it is hard. It is solid because the laws of quantum mechanics mathematically forbid the particles from overlapping. And that creates a repulsive force that my brain just interprets as touch.
You're not touching anything. You're feeling quantum repulsion. And that repulsion is incredibly powerful. It operates on an astronomical scale, too.
Like with dead stars, right?
Exactly. Consider a white dwarf or a neutron star. When a star exhausts its nuclear fuel, the outward pressure of fusion stops. So gravity just crushes the star inward.
And the atoms get crushed.
The atoms completely break down. The material becomes what we call degenerate matter.
Yeah.
Gravity is squeezing the star with just incomprehensible force, but the star doesn't collapse into a black hole.
Because of the Pauli exclusion principle.
Yes. The only mechanism holding up the entire mass of a dead star is the absolute refusal of those fermions to share the same quantum state. It creates this outward degeneracy pressure that counters the crush of gravity.
So the exact same quantum traffic rule that stops my hand from going through the wooden desk is strong enough to hold up a neutron star.
It's the exact same physics.
That is mind-blowing. But it brings us to what I think is the most jarring discrepancy in the sources.
Oh, the missing mass.
Yes. If matter is just tiny point particles with zero volume, kept apart by quantum exclusion, where does the actual heaviness come from? Let's just look at a single proton.
Okay, a proton is made of 3 quarks.
Right, 3 quarks. But if you isolate those 3 quarks and measure them, their combined mass only accounts for about 1% of the proton's total mass.
It's tiny.
It's like 12.5 mega-electron volts, while the proton itself is about 938 mega-electron volts. So 99% of the mass is just missing from the particles themselves. Where is it?
The remaining 99% resides in the binding energy of the gluons.
The gluons.
Yeah, gluons are the elementary particles that carry the strong nuclear force. They are what hold the quarks together inside the proton. And unlike gravity or electromagnetism, which get weaker as you pull objects further apart,
Like magnets.
right, the strong nuclear force behaves more like a rubber band. As quarks try to pull away from each other, the force between them actually gets stronger.
Oh, so it stores a ton of potential energy.
An immense amount. And those quarks are also moving around inside the proton at nearly the speed of light, so they possess enormous kinetic energy too.
Wait. But gluons are massless force carriers, right? Much like photons.
Correct. They have no mass.
So we have 3 tiny quarks contributing almost nothing and a swarm of totally massless gluons. But because they are interacting with such violent kinetic and potential energy, that energy manifests physically as mass.
That is the direct mechanism behind Einstein's E=mc².
Wow.
Mass and energy are equivalent. Confined energy is mass. The chaotic, intense interaction energy of the strong nuclear force inside the nucleons literally creates the vast majority of the weight you feel when you pick up a heavy object.
Let me make sure I'm getting this. You're saying that if I have a 100-pound person, 99 pounds of their body weight is literally just the turbulent, invisible binding energy firing back and forth between subatomic particles.
Yep.
So the actual stuff, the fermions, only accounts for 1 single pound of their entire body. It's like having an empty suitcase that weighs 50 pounds entirely because of the tension of invisible springs bouncing around inside it.
That's a great way to put it. And this equivalence holds true for macroscopic systems as well. Because energy and mass are the exact same entity, adding energy to a system strictly increases its mass.
Wait, any energy?
Any energy. Let's take exactly 1 kilogram of solid ice at its freezing point. If you add thermal energy to melt it into liquid water, the resulting water actually has slightly more mass than the ice did.
Even though we didn't add any new water molecules, we literally just added heat.
Just heat.
But heat is just the kinetic energy of the molecules moving around faster. How does that translate to the water getting heavier on a scale?
Because the thermal energy you added to break the crystalline structure of the ice, which is the latent heat of fusion, remains in the water as internal energy. According to E equals mc squared, you divide that added energy by the speed of light squared, and you get the corresponding increase in mass.
So how much heavier does the water get?
In the case of melting 1 kilogram of ice, the mass increases by roughly 3.7 nanograms.
3.7 nanograms.
It is an incredibly tiny amount because the speed of light is so large, but it is a real physical increase in the mass of the water simply because it is warmer.
So my body is mostly empty space, given the illusion of volume by quantum state exclusions, and 99% of my weight is just the chaotic energy of subatomic rubber bands holding my negligible particles together.
I know, it sounds like science fiction.
It's hard to imagine the physics getting more bizarre than that.
Well, actually, if you zoom out to the scale of the cosmos, the story of matter becomes significantly more humbling.
Oh, right, because we're only talking about a tiny fraction of what's out there.
Exactly. Everything we have discussed so far, the quarks, leptons, protons, melting ice, neutron stars, that all represents a minuscule fraction of the universe. To get the full picture, we need to look at what is missing, starting with antimatter.
Antimatter. Okay, so antimatter particles have the exact same mass as their normal matter counterparts, but they have an opposite charge.
Right. An electron has a negative charge, while a positron, which is its antimatter twin, has a positive charge.
And when they come into contact, they annihilate completely, right?
Yeah.
Converting 100% of their mass back into pure energy.
Which is incredibly efficient, by the way. But here's the mystery. According to our current models of physics, the Big Bang should have created exactly equal amounts of matter and antimatter.
Makes sense.
The symmetries inherent in quantum mechanics suggest there is no reason for the universe to prefer one over the other. But if that were true, all the matter and antimatter should have completely annihilated each other in the first fraction of a second of the universe's existence.
So the cosmos should just be a sterile sea of radiation
Yeah.
with no solid matter whatsoever.
None. But the fact that you and I are sitting here having this conversation and there is a desk in front of us means something broke that symmetry.
Baryon asymmetry.
Yes, baryon asymmetry. It is one of the most significant unsolved problems in physics. In the extreme conditions of the early universe, some completely unknown mechanism caused a minute imbalance.
How in it?
For roughly every 1 billion antimatter particles, there were 1,000,000,001 normal matter particles.
1,000,000,001.
Yeah, so the billions annihilated each other, filling the universe with the cosmic microwave background radiation that we still detect today. But that tiny fractional excess of normal matter, that one extra particle in a billion, survived.
So everything that exists in the physical universe today, every star, planet, and person, was built from that microscopic rounding error.
We are the leftover rounding error. But even that surviving normal matter is just a fraction of a fraction. The source outlines point out that all the surviving baryonic matter, every galaxy, every nebula, every black hole, and every human being only makes up about 4% of the observable universe.
4%. That's it. So what's the rest?
Well, roughly 26% of the universe is composed of dark matter.
And it's dark because it doesn't interact with the electromagnetic field, right? It doesn't absorb, reflect, or emit light at all.
Right. It's completely invisible to us. We only know it exists because we can measure its gravitational mass. We literally see it bending the light from distant galaxies through gravitational lensing, and we see its mass providing the extra gravity needed to keep rotating galaxies from flying apart.
It has mass, but it is completely invisible to our standard model of particle physics.
Exactly, which leaves 70% of the universe unaccounted for.
And that's dark energy.
Yep. That remaining 70% is dark energy. And while dark matter exerts a gravitational pull, holding galaxies together, dark energy acts as a repulsive force on a cosmic scale, causing the expansion of the universe to actually accelerate.
This is so humbling. Human beings have spent thousands of years analyzing reality. The ancient Greeks argued about fundamental elements. The Romans carefully measured carob seeds. Cavendish built a delicate torsion balance to weigh the earth in a shed. And modern metrologists built a Kibble balance to weigh reality against the speed of light.
It's an incredible journey.
It is. But after all of that effort, it turns out we have only been studying the 4% of the universe that happens to interact with electromagnetism. We're effectively blind to the other 96%.
We have mapped our 4% with astonishing precision, but the vast majority of the cosmos operates on rules and materials we just have yet to comprehend. However, the mathematics we developed to understand our 4% does offer some pretty strange insights into the fundamental nature of existence itself.
You mean Tashians?
I do. We've discussed normal mass, and we've discussed massless particles like photons and gluons. But quantum field theory also permits the existence of Tashians, which introduce the concept of imaginary mass.
Imaginary mass, meaning a mass value that, when squared, results in a negative number, just like imaginary numbers in mathematics.
Exactly. But in the equations governing quantum fields, an imaginary mass doesn't mean we have physical particles flying through space faster than the speed of light, which is how tachyons are usually depicted in science fiction.
Right, no faster than light travel. So what does it mean?
Instead, an imaginary mass represents a profound instability in a quantum field.
How does an imaginary mass create an instability?
Imagine a ball balanced perfectly on the very peak of a steep, smooth hill. It is in a mathematical state of equilibrium, but it is inherently unstable. The slightest perturbation, the tiniest breeze, will cause it to roll rapidly down the slope.
Okay, I can picture that.
In quantum field theory, a field at the top of that potential energy hill has an imaginary mass. The universe despises instability, so the field immediately undergoes a phase transition called tachyon condensation.
Tachyon condensation.
Yeah, it basically rolls down the hill to the bottom of the valley, settling into a stable vacuum state.
So the imaginary mass is really just a mathematical indicator that reality is temporarily out of balance and it has to shift to fix itself.
Exactly. And the Higgs mechanism, which is responsible for giving fundamental particles their mass in the first place, relies on this exact process. The Higgs field actually begins with an imaginary mass at the top of the potential hill.
Wait, so the Higgs field started out unstable?
Yes. As the universe cooled after the Big Bang, the field underwent tachyon condensation, rolling down to a stable, non-zero energy state at the bottom of the valley. It is interaction with this newly stable, condensed field that grants particles like electrons and quarks their normal positive mass.
So at the absolute deepest level of reality, mass isn't just an intrinsic property of an object, and it isn't just confined binding energy. Mass is fundamentally a measure of the stability of the vacuum of space itself.
That's a perfect way to summarize it. When a field's mass becomes imaginary, reality actively condenses until it finds a stable form again, locking the fundamental rules of our universe into place.
Look again at that desk or the steering wheel or your phone right in front of you. It feels perfectly solid. But that solidity is just a repulsive force born from the mathematical refusal of particles to overlap.
Yep.
Its weight is largely an illusion generated by the turbulent, confined kinetic energy of invisible forces. The matter that makes it up is a 1 in a billion survivor of cosmic annihilation, floating in a universe dominated by dark forces we can't even see.
It's a lot to take in.
And beneath all of that, the very mass giving it reality is just a leftover footprint of a quantum field that rolled down a mathematical hill to find stability. It really makes you realize that the everyday world we navigate isn't solid at all. It's just a remarkably stable, incredibly complex 4% illusion.